So any questions folks would like to go over that could be particularly helpful to start us off? Okay, so on this exam, the average was really quite high, and there was nearly a perfect score, off by 1 point. But let's take a breather, deciding if we want to look over a problem while I hand these out. Oh, yeah. Sorry about the poker face. As far as facial expressions go, I tried not to look at the grade when I hand back the exam. I don't know why I do that. Also, when I grade the exams, everyone's first page gets turned, and I grade the entirety of problem 1, then the entirety of problem 2, and so on. But any problems that folks would like to go over that might be particularly helpful to discuss? I didn't make any special comments on one I definitely want to go over. Well, other announcements that I want to make is that on this particular exam, keep in mind that once again you do have 2 scores, and the core score continues to be a very, very conservative score in the sense that your real score is probably higher in the course. We still haven't dropped the lowest 4 homework assignments. And the very end of the semester, this has been finally put in writing. At the very end of the semester, your final exam score, if it's higher, we're not going to lower people's scores with extra credit. If your final exam score is higher, it would replace the lowest of exam scores 1 through 3. And so that definitely hasn't kicked in yet as well. And if you're just curious about what your score could possibly be at the end of the semester, you could always go to the syllabus where there is this table down here that will show you what the breakdown is. Also, feel free to email me as well, and I have all your assignments and homeworks and exams put in an Excel sheet, and I could also look at that pretty rapidly since everything has been programmed in. What's harder for me to look at is dropping, say, the lowest 4 homework assignments, because that could cause some problems with the Excel. But you're also welcome to just email, say, hey, Mike, I just want to know what score do I have to get on the final in order to pass the class with 70% or higher? Anything like that would be just fine, and those emails are always welcomed. What other questions on the exam folks would like to discuss? Okay, other announcements I have so far today are that we are doing section 11.10 again. It's a giant section. And also, due to the weather and all sorts of interesting problems, there was a sick day that I took personally. It means we can't do 11.11. I'm sorry, folks. But we'll try to do a flare of application type problems from 11.10 as we finish out that section. This feels like the one section that has to go. So then our plans will be, after we do 11.10, we'll be back on track. And 10.4 being covered on Wednesdays of closed week is really just a pacing issue. We'll possibly finish 10.4 very soon on Wednesday, maybe even on Monday as well, since these sections are a little bit shorter. So when we come back on closed week, we'll be dedicating at least half of that week, probably closer to 2/3 of that week, just to reviewing for the final exam. And on the Moodle website as well, if you go to the very, very bottom, there is a sample set of final problems, and also be posting a sample final exam as well, the old exams for prior semesters. That's a lot of talking. Any questions at the moment about any of that? Okay, so another thing I changed on the Moodle website was this is now 11.10, and there's an indication on the final exam that although it is comprehensive, there's going to be an emphasis on these 5 sections in particular. And what we mean by emphasis is definitely at least, but probably around 1 problem would be asked per section on those. Whereas if we go to the entirety of every section we covered, I can't exactly ask 1 section, because then the exam would be impossibly long. So plan for at least 1 problem for these 5, and then it'll be representative but kind of scattered throughout the rest of the course that we covered. Does that make sense so far? I think I'm going for about 20 at the very most. And 20 sounds really like a lot when we just had a 75-minute exam with, what was that, about 8 problems? But some of these 20 questions are going to be a lot shorter. So although 20 sounds a lot like a lot, it's more of a granular exam, so there'll be some quicker problems. And that's also part of the reason for uploading old final exams, so you can see what the nature of a 2-hour exam might feel like and what the questions could look like as well. Other questions about that? Okay, so the final exam has not been written, but I'm going to shoot for anywhere between, I would say on the low end, 16, on the high end, about 20 questions. Other things we can discuss is that the final exam has finally been made final. The schedule is going to be in this class exactly 2 weeks from today. The difference is that we'll start at 8 p.m. and we go until 10 p.m. It's pretty horrible, but that's the routine schedule that's been going on for several years so far. That's kind of nasty. When I write this exam and when I grade this exam, I do keep in mind that everyone has been here from 8 p.m. to 10 p.m. to do an exam, so it's graded with those considerations. I try to avoid curving exams. This one was not curved, but I do sometimes curve the final exam because it's such a late exam you have to take. But aside from that, the exam schedule has been made current. This has been changed to 11:10, and I think that's all the announcements I had. Any questions from you folks then before we start our work today? Okay, let's start then. So we're still in section 11.10 on Taylor series and Maclaurin series. And the definition on the board is just the definition for what it means to have a Taylor series centered at A and what it means to have a Maclaurin series. But this section 11.10 is really rather large. Our goal today is to discuss binomial series, as well as table 1. It's a weird thing to say, but if you go to the textbook in section 11.10, there will be a table 1, and that's also posted on the Moodle notes in 11.10. So this is our table 1. We have several Maclaurin series for some common and interesting functions like e to the x, sine, cosine, and so on. And we can use these known formats for a particular Maclaurin series to represent common functions in terms of these formulas. That was really the entirety of a section 11.8. We took 1 over 1 minus x, the geometric series formula, and we found power series representations of many different functions. Sometimes we integrated or differentiated first. And we're going to do the same with the rest of that sheet here on table 1. So that's our goal so far. Any questions before we start? Okay, let's start with the binomial series then. So the first thing we're going to do is, almost as a review problem, we want to find the Maclaurin series representation of f of x equals 1 plus x to the power k, where k is any real number. Really anything at all. It can be 0, although that would be sort of silly to do, because 1 plus x to the power 0 would just be 1 itself. But we're going to allow k to be square root of 2 if you like. It could be 1/2, so we're taking the square root and so on. So we want to find the Maclaurin series representation of that. And notice what this is allowing us to answer as a question, finally, is the following. We have 1 plus x to the power k. If we set k is equal to 2, it would just be this. And we know that there is no exponent law for that. We literally have to use the definition of base 1 plus x to power 2 to get 1 plus 2x plus x squared. So there's no exponent law for that. But if we FOIL things out carefully, we would have an answer. And a very, very common question is, what are we supposed to do in this case when k is 1/2, for example? Or something else, maybe 1/3, 3/2, anything along those lines. There is no exponent law, so we can't FOIL it. And finally, the binomial series for f of x equals 1 plus x to the power k will tell us how that process should really go once and for all. That's a bit exciting. We'll see how to essentially, this is not quite the right way to say it, here we FOILed to get this result. We'll see what the analogy of FOILing is if the power is, say, 1/2. But first, we're going to start with the power series representation. Any questions with any of that first? Okay, so this first part is a bit of a review problem, but the final exam's in 2 weeks, so that's not entirely a horrible thing to do. If we want to find a Maclaurin series representation, then we just go to a two-column system. We look at f of x, we'll evaluate f at the center, but because it's a Maclaurin series, the center would be a equals 0 in this case. So we need to do these evaluations. In row 1, we'll have this, and row 2 will be the derivative, and so on. So f of x is meant to be 1 plus x to a power k, where k is anything you'd like. In that case, f of 0, that would just be 1 to the power k, but 1 to any power whatsoever is just 1. So that completes row 1, and then we'll continue until we have a pattern for the nth derivative at 0. Any questions with that so far? Okay, so really our whole punchline to the entirety of this process is we're trying to produce this. If we can get this, then we'll just fill it in by substitution, and the entire process would complete. We don't have to find the radius or interval of convergence unless the problem specifically says to do so. So first, we did the first row for f of x. Now we go to the derivative. F prime at x by the power rule. Here, k is just a constant. It can be any real number, but it's x that varies. That means by the power rule, we'll have k times 1 plus x to the power of 1 less, k minus 1. Then down to the opposite column, f prime at the center, we're still putting in 0 here, so this is always going to be 1 to some power. Even though that power changes, this is still a 1. So we get on this line just a k. And that's our first derivative. Any questions so far? Okay, so with this, if I have a pattern that goes 1k, it's really not clear what the nth term should be in this pattern, so we just keep on proceeding. So f double prime at x, we take k, the old exponent, it'll be multiplied by the new exponent, k minus 1, and the power on the old base, 1 plus x, will be now k minus 2. At this stage, it might look like something is going on, because we can say f double prime at 0, this will be k times k minus 1 times still a 1. So we have k times k minus 1. So if we had to guess on the third derivative, then we probably are able to guess on the nth derivative. Can anyone see what the third derivative should be based on the pattern of first derivative to second derivative, then to third derivative? Close. That is really close, actually. A factorial almost emerges, but it doesn't have all the parts. Say this one starts at k, this one goes k, k minus 1. For it to be a factorial, it'd have to end all the way at 3, 2, 1, all the way. But it's really, really close. When you say factorial, it means you're kind of thinking it should go k, k minus 1. And would you folks agree k minus 2 should be the very next factor? Yeah, that's essentially the pattern. It's not quite factorial because we don't have k minus 3, k minus 4, all the way to 4 times 3 times 2 times 1. But it's very, very close. And we're going to discuss a formula that relates this to the factorial. Other questions so far about that? Okay, another thing where it makes it not quite a factorial is keep in mind that k itself can be any real number. So k could have been a half, and we don't quite have a notion of 1/2 n factorial. For our class, this is undefined. But if you take a differential equations class or a statistics class, they would define that through use of the so-called gamma function. But with a 1/2 as a factorial, so far we don't have quite a function for that. But in either case, if we can make this as a prediction, notice that at third derivative, we have 3 factors. At the second derivative, we have 2 factors, 1 for the first derivative, 1 for the 0th derivative, so there's a bit of a pattern breaking there. But that means we can go off to the nth derivative. Those little parentheses around n just communicates it's actually a derivative, not a power, not a composition type rule. So the nth derivative at 0, it should have k factors altogether. So we'll start at k minus 1, excuse me, n factors altogether, k minus 2, all the way to k minus, I can't quite go k minus n. because then I would have n plus 1 factors altogether. Does that make sense so far? Like that's kind of tricky. If I go, say, for third derivative, I have k minus, not 3, but k minus 2. So for nth derivative, I can't go k minus n. It wouldn't exactly work. Third derivative, I have k 1 less. Second derivative, I have k not minus 2, but 1 less, minus 1. So similarly, this should be k, let me go with a bracket, minus, not quite n, but something else. Anyone see what should go in there to nail down that pattern? I heard minus 1. Folks agree with that? Yeah, it should always be k minus n minus 1 right here. But then we'll use the distributive law, so not always, just for the moment. So minus n minus 1, because we have the nth derivative, should be associated with 1 less on the final term there. So that's the pattern for the nth derivative right at 0. How does that look to folks so far? Does that look all right? Okay, so if we feel okay about that, then notice we've essentially produced the numerator of this quantity. So we're about ready to state the formula for this entire thing. So we can say, then, 1 plus x to the power of k is going to be equal to the summation as n goes from 0 to infinity of, well, there it all is. This is quite an object, and we have to divide it by n factorial. So what people have done down the line is they didn't use all of this. They have put in the formula for the binomial series, just because it looks nicer, k choose n. So this is a really weird object. This is not a fraction. There's just space between it. And we do use parentheses to just say this is all one entire symbol. And the way we define k choose n in this context is slightly different possibly from the formulas you might have seen in probability and statistics. But in this context, we define k choose n. This is read as k choose n. The choose comes from a particular counting type interpretation if k was a positive integer. Remember, k can now be negative, it can be a fraction, so its intuition of what it's meant to do does break down, but this is still something we can calculate. It'll be k minus 1, k minus 2, all the way to k, and if we use the distributive law, this would be minus n plus 1. I almost prefer this because it reminds me that this is an association with the nth derivative to produce n minus 1 here, but it's always simplified in the formulas to that quantity. That's divided by n factorial, and this is referred to as, this is the binomial coefficient which is used in formulating the binomial series down below there of k choose n. Then because we did a Maclaurin series, this entire thing in yellow has been replaced with k choose n. We do x minus a to the power of n, but a is 0, so it's just x to the power n. And we've done it. That's the Maclaurin series representation of 1 plus x to the power k. Any questions about that so far? Okay, as the instructions indicate, all we want to do is find that Maclaurin series representation. So the problem ends here. Let's add just a little bit extra to this for the sake of filling out a formula. Here, it turns out that r is equal to 1, and the interval of convergence is equal to -1 up to +1. So you could show through a series of tests. This is a lot of work, so we're going to skip it today. But that would be the radius and interval of convergence for 1 plus x to the power of k. And what this might remind you of is 1 minus x to the power of -1. We already did something along these lines. So if we have 1 minus x to the power -1, this is also 1 over 1 minus x. And this is the summation as n goes from 0 to infinity of x to the n. And this holds provided the absolute value of x is less than 1. That tells us the radius is 1. And the interval of convergence is from -1 to +1 as well. And this was by the good old geometric series test. So once we took something like this, really all we've done so far is we've extended the geometric series test to, now we have a positive sign here. X can continue to be anything, provided that it's in this same interval. And it does have a different format. The power is here, and it's constant. Whereas on this thing, the power is here, and it varies. Well, the power being constant and -1 is a nice extension of the problem that we solved down below. So the geometric series can be extended to the binomial series, which is the short of that. Any questions about that so far? Okay, this was a bit of an issue on the last homework assignment. If we want to find a series representation of 1 plus x to the power of 2, using this tool right here, it's actually quite a lot of work because we have to get it in the format that involves the -x. So we solved this problem by first just integrating the whole thing. Then we used this formula on the antiderivative, and we differentiated it. But what you could have done from the onset is just use that, and you can get it done in one shot. So that's a very nice theorem. Any questions at all about it? Okay, one downside about this theorem is that it is really tricky to use. And that's why we're dedicating practically an entire class to this one problem. It's worthy of it. One thing that makes this nasty to use is that the formula k choose n may or may not hold where n starts at 0. There might be a particular value where k choose n as a formula holds. So we might have to, say, write down a first term, then go from 1 to infinity with the k choose n as a formula. And that's extremely subtle to see exactly where the lower index should start. So a really good strategy in this context is, it's sometimes good to think of this in expanded form. This series is always equal to 1, so that's how the first term will always be no matter what. So if the formula you give down here does not produce the 1, then already we know that we don't have the right indexing. The very next term, let's say divide by 0 factorial, just so that we can see what the pattern is. And keep in mind, this looks like madness, but 0 factorial, by convention, is really 1. So we didn't divide by 0. Everyone is still safe. The next term in this thing will be altogether k, whatever k is, divided by 1 factorial times x. Then we get k minus 1, divided by 2 factorial, and we have x squared. And that pattern will repeat forever. Any questions about that? Okay, so for this particular type of series, the binomial series, although this is a really good formula, rho 1, the formula rho 2 is pretty necessary as well, just to make sure that we haven't tricked ourselves into using the binomial coefficient for a term it doesn't apply to. So I think we're ready to start exercise problem using that as a formula. Any questions before we give it a try? Okay, so let's start with something that looks like this. I want to analyze a function that is f of x equals 1 minus x to the power 3/2. So let f of x be equal to 1 minus x to the power 3/2. And it says to find the binomial series representation of f. Then that's it. We don't necessarily have to find the interval or radius of convergence, but we could if we really want to. The radius is always 1, unless we change what goes here in place of x. Okay, so that's our function f of x. And what we can say is, for our solution, let's use the 1 minus x to the power 3/2. I want the binomial series representation, so that will be a summation as n goes from 0 to infinity of k choose n times x to the power of n. So there it is. That's the binomial series representation. It feels like it should end there because that's what the formula says. That's the binomial series representation. But keep in mind there is some very, very subtle problems here. This k choose n as a formula has issues. We have to analyze it and make sure this equality is actually dead on accurate. So as a formula, saying it's always equal to this, well, that just depends on k itself. If you pick the wrong k, then this pattern cannot hold forever. So we're going to analyze it this way as well. On the other hand, 1 minus x to the power 3 halves is also equal to 1 over 0 factorial. Then it'll go plus k. But what would you say the k is in this problem? I'm going to delete this k, so if you're working in pen, you don't necessarily have to put it in. But let's see what that k should be in this situation at the moment. Yeah, whatever that power is the k value. Yeah, exactly. So 3 halves, this is kind of a waste of chalk. I mean, its only purpose is to help out with the pattern. So if you just wrote 3 halves, that'd be completely fine. And it's to multiplying x to the power 1. Then it'll go plus. Now we have k, 3 halves, times k minus 1. That will be 3 halves minus 2 halves, so 1 half, divided by 2 factorial times x squared. Then dot, 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 since there are infinitely many more terms altogether. So I only wrote down this row just as a check to see what terms I'm getting, to see if the formulas for k choose n is working out at every index, or which index it might work out at. So that'd be my very first step. All I've done is written down the formula. I've expanded the formula's first 3 terms, but the very next step is to actually expand k choose n and see what it's going to come out as in this particular problem. So that's where the heart of all the work is. But any questions with what we've written? Okay, so now next step, we're going to look carefully at k choose n, where the k is 3 halves. So k choose n is now, the k value is 3 halves, choose n. The index n is the thing that's going to vary in the series, so we'll leave it alone. And now at this stage, we write the formula. The easy feature of the formula is that the denominator should be factorial. So let's drop that down. Bottom, not the denominator, but the bottom of that particular symbol should always go to the bottom of the fraction. Then the numerator of, again, this is not a fraction, so shouldn't say numerator, but the numerator of this symbol is 3 halves. That's what goes here. So it'll be k, then k minus 1, then k minus 2, then k minus 3. But there's also altogether k different factors in this entire list. So this has k factors, excuse me, n factors. Let me circle the n there. So we have to make sure that we write n products all together. But as n changes, that's impossible to do. So instead, what we'll write is a nice device that says I have 4 factors that'll be multiplied by, and so on, dot, dot, dot. Then it's going to be multiplied by the very final factor, which is k minus n plus 1, if we decide to go with that as a formula over here. So there it all is. Now it's a big algebra problem where we're going to try to simplify this as much as possible with the goal of putting it into the power series and then double checking this partial list to see if it actually checks out as correct for every single term, or if we have to make this start at n equals 5, say. But questions so far with what we've written down? It's a bit of a mess when you write at this stage. Yeah, question? I could have gone to 4, say. I just decided with 3 factors or 4 factors, that's enough to establish the pattern I'm going to try to go for. I would say go for 3 at least. And the more the better, but then it becomes too much copying after some point. But because n is unknown, n could be 10 million, we have to somehow, at some point, put in the dot, dot, dot. What are the questions so far? Okay, so the 3 to 4 factors was really just a personal choice. I would say 3 factors at the minimum is a good way to go to nail the patterns down for finding a formula for this thing. Next thing we should do is, I mean, it is an algebra problem. Let's resolve these groupings in the numerator by order of operations. So let's do all the subtractions. We also want to be efficient about it. So let's say that this is 3 halves, choose n, not divide by n. It's now going to be equal to, and the first thing that we can work out, here, is there is a 3 halves as a fraction. We've computed this to be 1/2 already. And notice that we seem to be descending by 2 in the numerator. So I would check if this pattern holds with 3 halves. Minus 3 is minus 6 halves, which is negative 3 halves. And no, it does not. So there is a pattern breaking in there somewhere, somehow. Does that look all right to folks so far? Okay, so I get as the next term, we have a negative 3 halves. So from here to here, we descend by 4. But from here to here, we drop down by 2. So let me just check out this one. 3 halves minus 3. So if I go 2 over 2, that's really, 3 halves minus 6, which is negative 3 halves, which should have been this one. I feel like there might have been a mistake doing the fraction arithmetic on this. So I should have copied 3 halves minus 2. I think I must have grabbed minus 3, put it over 1, multiplied by 2 over 2. That's 3 halves minus 4, so that's negative 1/2. Exciting world of fractions. So that should have been a negative 1/2 over here. What got x'd. I'll put it in yellow. And now we're on our way. So yeah, it looks like the pattern of descend by 2 actually is holding. From here to here, I descended by 2. From here to here, I descended by 2. I could write the very next one ought to then be negative 5 halves, descending by 2. And the number of times we descend by 2, that's just the number of each of these factors, separated by parentheses. So we go all the way to the final one. 3 halves minus n plus 1. 3 halves minus 2n over 2 plus 2 over 2. If you mess up fractions once, you ought to go careful with the next ones. So this is the very last factor. And altogether, this is going to be 5 minus 2n divided by 2. So that 5 is interesting as well. Let's highlight that thing. Altogether, it's 5 minus 2n divided by 2. And the whole thing is being divided by n factorial. Okay, so that was one big step. All I've done is all the fraction arithmetic across the numerator. Any questions at all to that step? Okay, so the next thing we need to do is clean this up because it's still a gigantic mess. And the very next thing we can do to make it better is let's eliminate the fact that we have a complex fraction. There's a fraction with fractions in the numerator. We can fix that by factoring out 1/2. But there is n factors in this entire numerator. So this is what the factoring would look like. We have 3 halves, choose n, is equal to, down the denominator, I'm going to put the original n factorial. But now I have 2 to the power of n, because I'm pulling out 1/2 from every single factor in the numerator. And you can recombine that to the denominator of the original fraction. That's going to leave us with 3, 1, negative 1, negative 3, negative 5, all the way to ... 5 minus 2 to the n. So I pulled out all the divisions by 2 happening in the numerator. There was n of them all together. Still, there is more that we can do to this thing to simplify. But any questions to this step so far? Okay, so 3 halves choose n is always equal to this no matter what. So we have to, so far, copy that into here. But what is very questionable at the moment is if we can actually start at 0. So keep in mind, that's where this is going to support us. The very first term should have been positive 1, which occurs when n is 0. So if I put n is 0 onto this right-hand side, that would mean I have just one factor. And that would be found by putting in, there's 0 factorial in the denominator, 2 to the 0 denominator. We would put a 0 there, but that would give us a 5. we have a problem then, because we should get 1 as our very first term. So already this tells us this does not hold when n is equal to 0. So let's put that down just as note keeping. So n cannot be 0 for this formula. Then let's check out 1. If n is 1, we should be picking up a 3 halves and nothing else. And it should be positive at the same time. So let n be 1 in this formula. That would mean we still have one factor. It would be this as the very first factor here, where we put in a 1. We would get a 3. And if we got that 3, if not as positive, it looks like we're all good, because we also have 2 to the power 1 here, so now it's 3 halves. 1 factorial is just 1. So it looks like we're okay to start at 1. Or are we? How do you folks feel about this? Might be okay. I'm a little concerned with all these negative signs. That's the only thing that's going to possibly mess it up. Would you folks agree with that potential point of contention? If we're off by a sign, there could be a situation. So now you need to count the number of negative signs in this thing. So that's our next step. Everything we're doing here is motivated by the goal of getting this right. It's a frustrating set of steps you have to take, but when you see these in the homework, this is essentially the logic of everything that's happening. So now we're factoring out -1 a whole bunch of times to give us 3 halves, choose n, equals, I'm going to eliminate this one right here because multiplication by 1 doesn't change anything, and I no longer need it for any specific pattern. So I'm going to say that this is canceled. We had n factors, but there was 2 factors that came out positive. So I'm going to factor out the -1 sign from here, starting at this -1, all the way to the final factor. That means it would come in as a -1. What would you say the power should be to that thing? Kind of weird questions, right? They're all kind of counting questions. And that's what makes this really kind of strange math. The types of things we do is subtle. But the way you could count the negative signs on this one is, recall that k choose n. This will always involve n factors. So if this is k choose 0, there'll be 1 factor. That's the only one that's odd. If n is 1, then there'll be 1 factor. If n is 5, there'll be 5 factors. Here, there must be n factors. So I start by writing, there's really -1 to power n, but I'm only actually factoring from here to here where that lightly drawn bracket is. So what would you have to add as a correction to that, possibly, if anything? Would you folks agree maybe -2? Kind of a weird logic, right? Well, the reason for that was, remember, if I look at all these factors, things separated by the parentheses all the way to this one, there's really n altogether, right? But 2 of which were positive. So if I go to factor out the -1 sign off every factor that has a -1 sign, I'd be factoring out all the n except for the 2 that were positive. So it would be a -1 to the power n minus 2. That's really interesting because -1 to the power of n minus 2 is also equal to -1 to the n. Darn it. If it had been power -1 to the power n minus 1, then that would have been important. But if we're off by 2, actually there's no difference because positive negative oscillates in a pattern of length 2. So for example, if n is 1, this would be -1 to the power of 1 minus 2 to the power -1. It would balance at -1 here. 1 here would also balance as -1. And similarly for any index you choose. So specifically because we're off by 2 this time, it would simplify this, which makes it a bad exam problem because if you forget to check something, you would never be punished for that on this one. But if it was n minus 1, that would have been more important. So let's leave it as a n minus 2, and then we can simplify that on the next step if we'd like. Then the next thing that's happened is I didn't factor a -1 out of these first 2 factors, so I'm going to write this as a 3. I'm thinking of this one as canceling, so I won't copy it. then the pattern now becomes, in the bracket, 1, 3, 5. These are now going up by 4. This is a pattern breaker, so we can ignore that one. We're going up by 4 on these. So this one should be in 9 on the very next step. And it'll be multiplied, ... 2. I'm factoring out a -1 from this one, so you could write it as 2n minus 5 in that way. If you distributed -1 back inside, it would have been -2n plus 5, giving back the original thing. So now we have 2n minus 5 as the last factor here. It's 2 to the power n down below times n factorial still. Okay, so I think we finally have it. We just have to check for 1 indexes, will this actually hold? For 3/2, choose n. But any questions so far to this step, folks? Looks like the pattern from here to here is that we're going up by, I'm not sure. I thought by 4 for some reason. I think I might have been looking from here to here. My brain did something weird. This should have been a +2, and we were descending 2, so that should have alerted me. But it should have been a 7. Thanks for spotting that. Other questions or comments so far? Okay, so with this work done, we already know we can't start at 0 because of the issue with this 3 here. Or rather, if we put a 0, we would have gotten a +5, and that's it. So now we're going to check 1. If we throw a 1 inside here, we would get 2n minus 5, or just 2 minus 5 for a -3. So that should correspond to this. So we have a 3 up above. We're plugging in 1, so this will be 3/2 really. So that's working out for the 3/2. 1 also goes here, but that would give us -1 to the power of -1, which does produce a negative, and that's a problem. That should be positive. So we cannot use it when n is 1 either. N cannot be 1 to start it off. So now we check 2. Question? Yeah. Oh, you're correct. I missed that. So if we put in a 1 here, it would be -3. This is going to convert it to +3. Now it's 3/2, and 1 factorial is 1. No, you're right. It does work at 1. Thanks for spotting that. So we can start off at 0 and be fine. Other questions with that? So there's a bunch of negative signs bouncing around, which is problematic with this. The evaluations have to be very, very cautious. I think we're ready to start. Questions so far at all? Okay, so at 0, the trouble is we plug in 0 here, we get a +5 when we should be getting a 1. However, at 1, we would get a +3, or excuse me, I was looking at the wrong one. Excuse me, at 1 we would get a -3 right here, multiplied by a -1, so it's +3. A 1 there gives us +3/2, and we'll have x to the power 1 down the line. So it looks like we are ready to start at n is equal to 0. But keep in mind, if you did start with n is equal to 2, like we just about did, it wouldn't necessarily be bad if you gave me the first 2 terms. It would just be kind of a weird way to do it if the second term can be absorbed into this thing, which we just checked it can. So finally, we can say the answer by all of this work is that if you want to take 1 minus x to the power 3/2 and essentially distribute or FOIL like we were looking at down here before, then this is what you would get. We have to write down this term because the pattern doesn't hold at 0, so it's going to be 1. Then I was about to write this one down, but the pattern holds for the second term starting at n is equal to 1. So we're going to write this as a series, where there's also a ... Does that make sense so far? Okay, so we take the value where it's going, this 3/2 choose n will work as a formula by inspecting these actual terms, and we can write that this is 1 plus summation as n starts at 1 goes off to infinity of all of this as a one big thing. So this will be -1 to the power n. If we reduce this, it'll be multiplied by 3, because that's just a feature of 3/2 choose n. It caused a combo breaking pattern. But then we have 1, 3, 5, 7, or we can cancel this 1 if we'd like. So we have 3, 5, 7 still emerging. 3, 5, 7, ... 2n minus 5, and sadly, the formula has to go at this point. All of this is being divided by 2 to the n times n factorial, and there's still one last thing left. Anyone see what's missing from that power series representation still? Yeah, it still has to vary with x. It's a Maclaurin series, so we just do x to the power n. And that's how you can multiply out or expand 1 minus x to the power of 3/2. Turns into that exciting mess, where we had to start with 1 purely because of this pattern breaking right at that line. Well, other questions folks would like to discuss about this kind of problem? Okay, so that's the binomial series. As a formula, it's a pretty important one because it can be used in many, many different contexts. Sometimes you really just have to, in your problem, expand something like this. And possibly you may only need maybe the first 4 terms, and you can use that as a very decent approximation in a larger problem. So if you're doing something in differential equations, maybe you just need the first 3 terms, or possibly the first 29 terms, in which case this is more valuable to have the entire representation. But let's go off to a slightly different kind of problem. Unless there's any questions or comments about this one? Yeah. Oh, you're saying start at -1, and you're looking at this line right here? The trouble with that is if you reindex at -1, you also have to reindex this right here, which would change the format of this as a formula. So it would work, you in fact could say start at any number you would like, but if you reindex to start at n equals 1, this would have to immediately reindex too. And the way it reindexes, if we say that this is the summation as n goes from 1 to infinity, then this would be k choose. We went from 0 to 1, so we increased by 1. So it'd be k choose n minus 1, x to the power of n minus 1 as well. So the problem could be worked out in that way. But it would give us the same sort of problems, just different looking algebra down the line. Other questions about that? Okay. Other questions or comments folks would like to discuss about this kind of problem? Okay, maybe let's do one last problem then and call it a day. Or maybe a couple problems, depending on how time flows. So for this second problem, it's going to say to find a Maclaurin series representation of, let's let this function be f of x equals x to the power of -3 times, how about sine of x minus 1. Okay, so we want a Maclaurin series representation of that thing. That could be kind of a nasty problem potentially, using table 1. It's really weird instructions. If this was an exam problem, the instructions would probably say, find a Maclaurin series representation of this function using, then they would just tell you what the Maclaurin series representation of the sine function would be. I think that's a better way to do this problem as an exam question. But as a homework question, this is okay, I would say. If you see this in the homework assignment for 1110, then just go to table 1 in the same section, and this is what you'd be faced with. So the book has collected throughout the several chapters in chapter 11, sections rather, all the Maclaurin series that we picked up, starting with a geometric series, and the problem is referring to a representation involving sine. So I would skip down to this right here from table 1, and that's where I would start in this process. So by table 1, what it produces for us is that sine of, I'm going to write it a slightly different way. I'll write sine of a, where a is going to be just some independent variable. I like to think of it as representing anything you like. It's going to be the summation as n goes from 0 to infinity, negative 1 to the n, a to something odd as an exponent, 2n plus 1, divided by that odd thing as a factorial, 2n plus 1 factorial, and the radius of convergence is infinity. So that's what table 1 would produce for us. And now we're dealing with x power negative 3 sine x minus 1. Anyone see how to start this kind of problem then, so far? I would say that this is the full statement of the problem at this point. It looks horrible, right? We have to somehow tie together this Maclaurin series representation of sine at a with this random f of x. But what we could do to start it off is start by just trying to make our function f of x look like the Maclaurin series formula. So we could say that f of x is 1 over x cubed, if we like, times sine of x minus 1, and we're going to use the Maclaurin series formula right exactly here, where the x minus 1 is just simply going to be inserted here and here. So if we do that, then we've effectively used the table 1. The radius was infinity for this, so it doesn't matter what value x takes. We are not changing the fact that the radius is still going to be infinity. Other questions so far? Yeah. Exactly, yeah. We're going to throw this in as a formula, and then there'll be 1 over x cubed that will try to work into the problem if possible. It's sometimes possible, but not always. This one's kind of a weird looking one. So let's first start off by saying this is now equal to 1 divided by x cubed times summation as n goes from 0 to infinity. And using table 1, really this is the only position where there's a change. So we'd start by copying negative 1 to the power of n, divide by still 2n plus 1 factorial, and something gets the power of n. It would just be the x minus 1. All we're really doing is evaluating this as a formula with x minus 1 as the input. So it would look about like that. Other questions with that so far? Okay, what we'd like to do if possible then is maybe something along the lines of simplify it as much as possible. However, x minus 1 to the power of n divided by x cubed really can't be simplified in any meaningful way without expanding x minus 1 to the power of n, but that's more binomial series stuff, so you may not want to do that necessarily. I would probably say this would be a decent stopping point. So these are interesting questions when there's really not a lot to do. I mean, you could do one extra step, but this is more of a stylistic choice where you could write your answer as negative 1 to the power of n, x minus 1 to the power of n, no cancellation, and down below is x cubed times 2n plus 1 factorial. So that would be the power series representation of that function. Yeah? Oh my goodness, it must have just completely got miscopied over. Thanks, 2n plus 1. That was a bad copy from here. Thanks for spotting that. Other questions with that so far? So probably the best thing to do if you're evaluating a formula is make sure you have the formula completely copied over, and then everything should go okay. Thanks for spotting that. Other questions about that one folks would like to discuss? So problems involving table 1 really kind of go this way. There's not a ton to do. How about one more like this? Does that sound all right to folks? Okay, so this one is still going to use table 1. The instructions are a little bit different. But starts off by saying, show that e to the power of I times pi plus 1 is 0 by first showing that e to the ix is equal to cosine x plus I sine x using table 1. Okay, so that is our application for table 1 so far. We could prove some really cool formulas. We want to prove e to the I pi plus 1 is 0, but first we need to show that this is an identity. And that kind of gives us a hint on how to use table 1, because table 1 has information on e to the x, sine x, and cosine x. So we can get a power series representation for all three at once. I'd probably, for this particular question, start with e to the ix, because if we simplify this first, we'll see that the right-hand side wouldn't merge. But there could be many different ways to do this kind of problem. You could start on the right and work it out till it becomes the left side. But we do have I in there, and I think this is the first time we've really honestly worked with I in this class. So let's just write a quick list to start us off, where I is the square root of negative 1, which implies I squared itself is negative 1. We're going to need lots of powers of I, because we're going to plug ix into that second formula, where we'll square it, cube it, raise it to the 4th power, and so on. So I cubed is just I times the list above it. So this will be negative I. I to the power 4 is negative I times negative I, which would be positive I squared, which would be negative 1. Then the table starts to repeat. Positive 1. I think. Yeah, so if I multiply this by I, it's negative I squared. I squared itself is negative 1, so that would be positive 1. Had to double check that, which means I to the power 5 is I to the power 6 is I squared, which is negative 1. And this will repeat forever. And that gives us some powers to work with. Any questions about that table to the right? Okay, so now we're ready to start with e to the ix. Doing essentially what we did, we can say that e to the ix is the summation as n goes from 0 to infinity of, we're taking the ix and raising it to the power n in that formula, dividing the entire thing by n factorial. So that is formula number 2, where the radius of convergence is infinite. Then we need to do something. This is where it gets interesting. Note that we have I to a power n, and that's where this table starts to support us a little bit. So writing out I to a power n could be one of 4 different possible values, either I, negative 1, negative I, or positive 1. So that means this can potentially change quite a lot. So let's expand it out. E to the ix, starting at 0 would give us 1 in the numerator. 0 factorial is also 1. So I'll get 1 over 0 factorial. You don't have to carry the 0 factorial. This is really just for narrowing down the pattern and the next steps. So that's optional. Then we go to index 1. So this will be ix to the power 1 plus I, 1 factorial times x. And then the powers and the factorials just increase by 1 down the line. So now it'll be plus I squared divided by 2 factorial times x squared plus I cubed divided by 3 factorial times x cubed. And we just have to decide how many terms do we really need. But because we're trying to show an identity that involves cosine x and sine x, which are 2 other power series entirely, I'd probably go for maybe 6 terms on this one, which means just 1 more. Then it'll be plus I to the power 4 divided by 4 factorial, x power 4, maybe a couple more just for good measure, plus I to the power 5, 5 factorial, x to the power 5, plus I to the power 6, last one I promise, 6 factorial times x to the power 6 plus, and then that goes on forever. So that would be e to the ix. Next thing I'd like to do is use this column on the right-hand side to start dealing with I to a power. There's really only 4 options, so we can start simplifying these down and produce still more patterns. Questions so far to this step? Okay, let's deal with the I to the power 0, that one's already done, all the way to I power 6. Well, we can now say e to the ix is equal to 1 over 0 factorial plus, nothing to simplify here, I over 1 factorial times x. But I squared is now finally something we can do. I squared is negative 1. So something happened. We have negative 1 over 2 factorial x squared. I cubed is negative I, so this is minus I over 3 factorial x cubed, and I to the power 4 is positive 1. So now it's plus 1 over 4 factorial, x to the power 4, and this is how we're going to alternate. It's going 1i, negative 1, negative I, positive 1, then after that, power 5 is going to be positive I, and so on down the line. So we could just replicate that entire list to get all values. So 1 over 4 factorial x to the power 4. Now we do I to the power 5, which is I, plus I divided by 5 factorial x to the power 5. Then the next one is going to be negative 1 for I power 6. So minus 1 over 6 factorial x power 6. The next term will be plus, and, well, maybe, so on down the line. But questions so far to that step? This is a weird problem where most of everything I'm doing is just copying. All I've done really from that last step to the next is use that table on the right everywhere I see an I. But now we have an interesting situation where we can do a rearrangement on this thing. We have infinitely many terms. We have some terms that involve I, so complex value terms, and we have some terms that involve just real numbers. So we also have real number terms at the same time. We should be careful about rearrangements because rearrangements can change the value of the total sum unless it converges absolutely. And in fact, it does. The ratio test was used on this, so that is a radius of infinity where e to the x will converge absolutely. With absolute convergence, you can reorder this in any list you'd like, and you won't change the value of what it converges to. So that's really the special deal with absolute convergence. If this was a conditional convergence, I cannot change the order that I write these terms at all. If I did, I could potentially make this come out to whatever summation we would like. That sounds kind of crazy, but you could check out 11.6, and they do exactly that for you at the end of that section. But let's now start grouping this. We're going to rearrange this into one infinite list involving the real parts. So this will be e to the ix equals, I'm going to use brackets to organize this, and every other one is a real term. So I'll start with 1 over 0 factorial, or just 1 if you prefer, then skip over to minus 1 over 2 factorial, x squared. Then we skip over to positive, so it's alternating, 1 over 4 factorial, x to the power 4, then minus 1 over 6 factorial, x to the power of 6, and there's infinitely many terms, so the plus dot dot dot, I would say that's really important. It captures the nature of this being an infinite sum. This is half the list, but it's also an infinite list. I just grabbed all of the even terms corresponding to even powers on x. Then we do it again. Let me grab everything that involves I. So we'll go plus. The only terms I didn't grab was this one, well, I didn't grab infinitely many of them, this one, and the one for power 7. So let's do that next. But notice every one of those circle terms involves I. So due to convergence, we can just factor it out. So I'm going to factor I out of infinitely many terms. Because it converges, we're OK. We can start by saying that this is maybe just an x divided by 1 factorial if you prefer. The next one is going to be negative x divided by 3 factorial, negative x cubed, then plus x to the power of 5 divided by 5 factorial. Then I didn't do the 7th term, but if we're going positive, positive, I guess the next is negative. We're doing every other term, so this should be x to the power of 7 divided by 7 factorial. Then we go plus dot dot dot. Just to remind ourselves again that that's the second half, which is also an infinite list. What questions so far with those two lists? Okay, so if we look at the very first list in brackets, what is that really? Yeah, that's the cosine. If we look at cosine and expand it, we would have 1 minus x squared divided by 2 factorial. And if you look at all those terms, it's all exactly there. Across from the I in green, that is sine, which we just got done working with. Sine involves just odd powers and also alternates just like we have. So we have two power series representation. This one is cosine. So by table 1, e to the ix is equal to cosine of x plus, we factor out I from infinitely many terms, and what emerged was sine x. So So now we have a really interesting representation of e to the power ix. There's different ways to write complex numbers. We have a rectangular form, a polar form, and this is the exponential form. Of complex numbers. Then we can say the original identity, e to the I pi plus 1 equals 0, it can be done at this stage, since we can say e to the I pi, maybe put some symbols here to say, by all this work, therefore, e to the I pi is now equal to cosine pi plus I sine pi. Cosine pi is equal to -1, and sine pi is 0. So now we have e to the I pi is -1. Adding 1 to both sides of the equation tells us e to the I pi plus 1 is 0. And that's a really cool formula. It has really no specifically nice purpose other than it just looks cool. So people gave it a name. They called it Euler's formula, or Euler's identity. Well, Euler has invented so much stuff. Who knows what it's really referred to, but Euler did it. That's his identity. Let's go with identity. Any questions about that problem so far? So that's one of the many, many exciting applications of Taylor series and Maclaurin series. If you go on to take differential equations, you may do this stuff, depending on who you take it from. So depending on how much you like it, you may or may not like to take it by Dr. Chen. Dr. Chen is an amazing instructor, but he goes pretty deep into this stuff in the differential equations class. So that's where you probably see it very next. But if you have questions, feel free to stick around. I'll be happy to help.